Hello, students. Very good afternoon. So, I hope the screen is visible to all of you. Let me check whether the recording is on or not. Okay. So, in the last class, we have discussed about the steady state equations, steady state conditions for the conduction, heat conduction. Now, today we will discuss the three-dimensional heat conduction equation. Three-dimensional heat conduction equation. So, in Cartesian coordinate system, one-dimensional heat conduction equation is when the heat is not generated within solid is simply d by dx into dt upon dx. So it becomes d square dt upon dx square equal to 0. So you can, and similarly the in cylindrical coordinate it's become d upon dr into r dt upon dr. Now, three-dimensional heat conduction equation, we will derive the three-dimensional heat equation as usual in the case of one-dimensional equation. Suppose we have taken Cartesian coordinate system, and in that system there will be we have taken a parallelepiped component. So that component has thickness dx, dy, and dz, and similarly qx is the heat conducted from the face ADHE, and qx plus dx is the heat leaving at the face BFCG. Similarly, in the y direction, it is Qy entering in this element. Heat is entering the element through the face DCGH and leaving ABFE. So what, what will be the volume of this element? It's simply dx, dy, and dz, and whatever the net amount of heat is, uh, net rate of heat conduction into this element from these three direction, x, y, and z direction. It's simply q net is equal to qx plus qy plus qz minus qx plus dx minus qy plus dy minus qz plus dz. And the simultaneously, if the heat is generated into the element at the rate of g watt per meter cube, then we calculate the total volumetric heat generation rate. Q gen is simply d into multiplied by the volume of element, that is dx dy into dz. Similarly, the rate of change of internal energy of this element, differential volume, that will be the stored within the system rate of change of internal energy. It's simply del E upon del T, del E upon del T, and this can be calculated as simply heat capacity of this element m into c multiplied by the changing temperature with respect to time. So m c del T upon dt. Now what is m? M is simply, we can by mass of this uh, element, and we can simply calculate this by multiplying the density into volume of this element. So it's become rho dx dy dz into c del T upon dt. Now, simply just apply the energy balance and you will get this relation. And ultimately, we will get this three-dimensional acceleration, three-dimensional heat conduction equation. And this three-dimensional differential equation for unsteady state, unsteady state heat conduction for NGO, an isotropic material. Okay. So in this equation, you can see it involves thermal conductivity and heat generation, density, and heat capacity. So also the functional relation that is used in this equation. So T is the temperature and it is the function of position, space, and time. So it is obviously it is x, y, z, and t. Similarly, heat generation, that is small g. It also the function of space and time, x, y, z, and t. T is the time, and conductivity also is the function of space. That is the for an isotropic material, this thermal conductivity varies along the direction. So it is also the function of, and capital C is the specific heat of the material, specific heat of the material. Just specific heat of the material, and it is quantified in joule per kg Kelvin. And rho d, rho is the density, density of material, that is measured in kg per meter cube. So Kx, Ky, Kz are the thermal conductivities. Conductivities in x, y, and z direction. In x, y, z direction. Hello, Nathan.
Hi sir, good morning sir.
Okay, okay. So basically, we are deriving the relation heat transfer equation, three-dimensional heat transfer equation for conduction. So we have already derived this equation del x, kx del t upon del x plus k del y upon del y, ky dt upon del y plus del by del z, kz del t upon del z plus g is equal to rho c del t upon del capital T upon del t. Okay, so this is the generalized three-dimensional equation, three-dimensional time-dependent differential heat conduction equation with heat generation and variable thermal conductivity. So in this relation, there are these parameter involved, and uh, temperature is function of position and time. Heat generation G, heat generation we have taken watt per meter cube. So unit of this is watt per meter cube. Okay, volumetric heat generation per unit volume. And C is a specific heat of the material, joule per kg Kelvin and density. So and Kx, Ky, Kz are the thermal conductivity of material or element in respective direction in x, y, and z. So this equation, this is the generalized equation, standard equation that can be used for the three-dimensional Cartesian coordinate system. Now, if we simplify by putting certain constraint one by one, suppose we have taken isotropic material. For isotropic material or element element. Okay, so what is the meaning of isotropic materials? It's kind of material in which thermal conductivity is constant in all direction, it doesn't varies. So it means for isotropic material, for case 1, kx is ky and this is equal to kz, and we can simply take as k. Now, when we put this relation, this condition in our generalized equation, so what happened in this case? Because k becomes constant, so you can take outside of this bracket. So simply your equation just converted into del square upon del t, del x square plus k del square t upon del y square, del square del t upon del z square plus g plus rho c delta t rho c del T upon del tau. And when we divide this K, this equation with thermal conductivity, you simply get del square T upon del X square plus and rho C upon K we can write as 1 by alpha, because rho C upon K, it's another parameter that is called K upon rho C is thermal diffusivity. Okay, so we can use this group of parameter K rho C. We replace three parameter with one parameter that is called thermal diffusivity of the material. So generally, so this is the equation. Three-dimensional differential equation for the transient heat conduction with constant thermal conductivity. Okay, you can say it is the governing equation for heat conduction. Now the case second. In second case, if we assume there is no internal heat generation within the material, for that case the value of G becomes 0. So uh, this term becomes 0. So our equation converted into simply for no internal heat generation. Internal heat generation. Del square upon del square T upon del X square. Just just wait a minute, Nathan. चार्जर इसका नहीं कर रहा है। नहीं है चार्ज। चलेगा। अब कुछ करिए। चलो ऑप्शन में है ना। बात नहीं रहा। So now the third case is the steady state condition. What is the meaning of steady state conditions? When the temperature is not varied with the time. So del T upon del T is equal to 0. So in the previous case, this right hand side of the equation becomes 0. So you will simply get the condition del square T upon del x square plus del square T upon del y square plus del square T upon del z square plus g upon k is equal to 0. So this equation is called Poisson's equation. So this is the Poisson's equation. So this equation is three-dimensional differential equation for a steady state heat conduction with constant thermal conductivity. Now, if in the material there is no heat generation, so it becomes fourth case, steady state and no heat generation. Steady state, no heat generation. For steady state and no heat generation. So simply your equation gets converted into del x square plus and this equation is also called Laplace equation. So this equation is called Laplace equation. Okay, so these are the equation that is applicable for the Cartesian coordinate system. If we change the coordinate system, like we take cylindrical coordinates or spherical coordinates, our equation becomes different. So we can just you just see here. This is a cylindrical coordinate system. So we are not going in detail derivation of heat conduction equation is for the cylindrical coordinate. We just generally explain the terminology and write the main equation directly. So you can see when we taken cylindrical coordinate system, so in that we just take a cylindrical element, differential element, this cylindrical element, and when we just in take the enlarged view of this, so you can see here, this is the volume element. So one will be the radial direction, other one will be the tangential direction, and so x, y, and z three dimension when we converted into r theta system. So r theta and z. So here the coordinate becomes r theta and z direction. R theta and z direction. The in analogy with the x, y, z in Cartesian coordinate system. Okay. So its thickness you can see here r dr, this volumetric element dr, r theta, and dz. So there will be three dimension dr, r d theta, and dz. Okay, this is similar to the x, y, and z direction. Now when we just apply the heat balance equation and calculate the net rate of heat conduction in going just coming to the element and leaving to the element, and then take the energy balance and apply uh, net rate of heat conduction. So after applying the energy balance, we will get this final relation. So here del square t upon del r square plus 1 by r del t upon del r plus 1 by r square del square t upon del theta square plus del square t upon del z square plus g by k is equal to 1 by alpha del t upon del t. So this is the generalized equation, three-dimensional heat conduction equation in I mean to cylindrical coordinate system. When we just transform this equation to rectangular coordinate, we can use this relation x is equal to r cos theta, y is equal to r sin theta, and z is equal to z. So we can equation we can also obtain by transforming the rectangular coordinate using this relation dx dy. Okay, so when we simplify this equation as compared to that, is the screen is visible, Nathan?
Yes, visible, sir.
Okay. So similar condition we can impose on this heat transfer in cylindrical coordinate also, just like steady state condition and heat generation without heat generation. So when we take the one dimensional heat conduction equation in radial direction, okay, so case First case, this is the important steady state one dimensional in radial direction. So it's become del square T upon del R square plus 1 by R del T upon del R plus G upon K is equal to 0. And we can also write this equation, but just taking 1 by R del upon del R and combining R del T upon del R. These are the both equations are similar, and if there is no heat generation, for no heat generation, so our equation becomes simply del upon del R, R del T upon del R becomes 0. So this is the important when we are interested to calculate the heat transfer in radial direction uh, in cylindrical coordinate system when there is no heat generation, okay, and the steady state heat is transferred in the steady state manner. Similarly, we can also derive the equation for the spherical coordinate system. So uh, in a spherical coordinate system, our coordinate becomes uh, dr r theta and r sine theta d phi. So here our element becomes r, theta and phi. There will be three direction, r, theta and phi, and sides of elements becomes, in this case, sides of elements becomes dr, r d theta and r sine theta d phi. These are the sides of cylindrical element, sorry, spherical element. So this is the r sine theta d phi, this one, this is r theta, and this is the dr. Okay. So method of derivation is same. It's similar to the cylindrical coordinate system. So you can just write this equation. So here 1 upon r square, 1 upon del r square del t upon del r plus 1 upon r square sine theta del by del theta sine theta del t upon del. So this is a long expression. So we will just explain a generalized method for remembering all these form. In previous for only one in one dimensional coordinate system. So now how we solve these differential equation? As you know that heat conduction equation involve differential equation. So obviously for solving these differential equation, we need certain conditions, initials and certain boundary condition for obtaining the exact solution of these differential equation. So for that, there are some predefined initial boundary conditions. So we learn that these boundary condition, how we put the condition, and it will be useful to finding the solution that depends on the physical condition existing at the boundaries of the medium. So first thing, first uh, we have taken the mathematical expression of thermal condition at the boundaries of an object. So this is called boundary conditions, and the boundary conditions we get from several common physical effects. Okay, which we just expressed in the mathematical form. So suppose we have taken the heat flux. Okay, uh, thermal boundary condition for this case for the plane wall that has a thickness L, and the left face, left face means in our coordinate system t and x coordinate system. So left face, this is the left face, and at this face value of x is equal to 0 because we are measuring the x from this point. So at x equal to 0 and at given time, the temperature of this wall is taken as T. So our boundary condition becomes at x equal to 0 and T is equal to 0, Txt becomes T1. So it is at maintained at a uniform temperature T1 when the x coordinate is 0, and that means left face. On the right face, similarly on the right face we have taken temperature T2, so we can uh, express the boundary condition in mathematical form as at x equal to L, T is equal to 0, T becomes T2. Okay, so this is the prescribed temperature boundary condition for a plane wall of thickness L. Again, prescribed boundary condition for heat flux flowing through plane wall of thickness L. So here the heat flux is flowing from left to right direction. So at the left face, when x is equal to 0, heat flux Qx becomes Q naught, and at x equal to L, Qx becomes QL at the right face. Now, if the direction of heat flux at the right face is opposite, that is, it means from uh, right to left, then this L becomes, you can taken as the negative direction. Just change the direction and you will get the uh, condition for the heat flux. Now, if we take the insulated boundary, so this is the special case of heat flux, prescribed heat flux boundary condition. This one. So there are two special cases of heat flux boundary condition. In one, in which the one phase is insulated. So in several engineering problems, the system boundary is insulated just in order to minimize the heat loss from the system. So we just assume for that case Qx is equal to 0 and they equate it with the Fourier equation law of heat conduction, that is kx dt upon dx equal to 0, and after equating it, you will get the condition dt upon dx is equal to 0. Al- Although in actual case there is no perfect case of perfect insulation, always there will be the loss of heat flux, but we can assume this condition, insulated boundary condition, for simplifying the problem. Another important criteria is thermal symmetry. What is the meaning of thermal symmetry? So in some situations, the boundary condition that is imposed on two sides of plane wall or solid cylinder or solid spheres that are identical, then we heat flow from center to two sides is also identical, and center of the plane is treated as a plane of symmetry. So for that case, how we just express the mathematical condition, boundary conditions. So simply you can see at R is equal to 0. For the case of solid cylinder that is exposed to the convection environment at its outer surface, so you will see here dt upon dr is equal to 0 at R is equal to 0. So R is equal to 0 means center at center point. And for the case of plane wall, dt upon dr, that is the temperature gradient at center, becomes 0. So this is the thermal symmetry condition, boundary condition. It just remember this condition. It will be very useful while solving the numerical problem based on heat conduction in one dimension. Now, another boundary condition is convection boundary condition. It means that is used for the balancing the surface energy. Now, in this case, convection flux from the fluid to the surface, this is equal to the heat flux conducted into body from the surface. So this is important condition. Whatever the heat flux is conducted via conduction, and it is equal to the convection for uh, from the fluid to the surface. So in mathematical form, you can just write as, suppose this is the case where plane wall is exposed to the convection boundary at both sides. You can now see this is the plain wall and it is exposed on the both sides where the temperature is still ambient temperature of fluid is T infinity 1 and other side T infinity 2. H1 is the convection coefficient at the left hand side. H2 is the convection coefficient on the right hand side, and the K is the thermal conductivity of the material of the wall. So at the left face when x equal to 0, whatever heat is conducted through convection, that is equal to H1 T infinity 1 minus Tx naught, and that heat, that flux, heat flux must be equal to the heat flux conducted in the plane wall from the surface. So this is the relation for the left hand side, and this one is the so this is for the right hand side. So boundary conditions can be written for cylinder and sphere. So this is the boundary condition, convection boundary conditions at the faces of the plane wall, and similarly we can write the boundary conditions for the cylinders and spheres also. Next one is the radiation boundary conditions. Just wait a minute. So in radiation boundary conditions, we apply the same concept as we have applied for the convection boundary condition. So heat conduction due to surface, we equate this heat conduction to surface with the heat transfer through radiation from the surface to the surroundings. So suppose when we consider the radiation boundary from the both surface for the plane wall, take you can see from this picture. So whatever the radiation heat transfer from surface to surroundings is equated with the heat conduction. So on the left hand side, heat will be conducted minus k dt upon dx at x equal to 0, and this much equal to the sigma epsilon 1 t naught or t infinity raised to power 4 minus t x is x at x equal to 0 raised to power 4 t4. And the right side, it's similarly k dt dx at x equal to L is equal to sigma epsilon 2 Tx temperature at x equal to L raised to power 4 minus ambient temperature raised to power 4. The temperature in radiation calculation must be used in Kelvin, not in degrees Celsius. So this point is very important while solving the numerical problem. Just convert the given temperature into Kelvin scale while using radiative heat transfer. So now interface boundary condition. So suppose there will be the composite wall. There is a composite wall. Then the interface boundary condition becomes important while solving the heat conduction problem. So boundary condition at interface of two layer is simply just heat conducted at on the left hand side is equal to the heat conducted on the right hand side. So on left hand side, we just see that we use the conductivity of first layer 1, and on right hand side use the conductivity of layer 2. So at x equal to at a, heat conduction equation is minus ka dt upon dx, and this is equal to minus kb dt upon dx at b, and the temperature variation at x tax is equal to tdx. So these two boundary conditions are very important. And so this is the very common situations generally occurs in day-to-day life, and the boundary condition also will change. It will depend on the situations. Boundary condition can be designed just by applying the energy balance at the surface, that is rate of heat entering in is equal to rate of heat entering out. So rate of heat entering in and equal to rate of heat entering out. So this is the important boundary conditions. Now we will solve some numerical problems in the next session based on these boundary conditions and uh, heat generation. Without heat generation, we will solve the conduction problem. So we will meet in the next session at 3:15. So I just close this session here. Nathan, are you in team?